Hi, welcome to Chemie 448 Lab in Dr. Young's class. We're Group 1 on Monday, and today we're going to be showing you the gas absorption lab, and then here's our team.
My name is Chris Hagist.
My name is Zach Sharpley.
My name is Abdul Freddy.
My name is Shantaro Nishi.
My name is Justin Chase, and today we are discussing CO2 adsorption. CO2 adsorption is very important beyond this experiment, as CO2 is currently the main cause of global warming. Everyone should be concerned with carbon dioxide, as it constitutes more than 60% of the greenhouse gases that cause this warming to occur. The figure below shows how CO2 has been increasing in the atmosphere from 1980 all the way to 2009. Humanity cannot continue down this path without consequences occurring. This is where CO2 adsorption comes into play. Absorption, coupled with absorption, has been proven to be the most suitable for post-combustion power plants to capture CO2. This is important as it allows carbon dioxide levels to decrease in the atmosphere, as it will be recaptured by these power plants and used and recycled. There are many different physical and chemical adsorbents that may be used during this process. These are summarized in the flow diagram on the right. While this is the broad picture of what CO2 adsorption can be used for, please allow Zach to inform you on what specifics we hope to gain from performing this laboratory.
Gas adsorption is an important separation process. In this experiment, we will be characterizing adsorption and desorption of two gases, carbon dioxide and nitrogen, and we will be using the lab data to characterize these into three isotherms. These isotherms will help us to relate and compare separation processes.
In order to execute this lab, we have created an isolated apparatus connected to three gases, argon, nitrogen, and CO2. The apparatus contains two individual chambers, one containing a 10-gram sample of carbon. The key aspect of this apparatus is that it contains many valves and two pressure gauges. This allows us to systematically pressure up the entire apparatus and each section of it, depending on which valves we open and close, and measure the individual pressures subsequently.
For this procedure, we will begin by pressurizing the C2 cell. Upon pressurization, we will open the valve, equilibrating the two cells. We will measure pressure systematically, and then isolate the C2 cell again by closing the valve, repressurize, and continue at incremental pressures. For desorption, the reverse is true. We will depressurize the C2 cell, equilibrate, measure pressures, isolate the cell again, depressurize, and continue at decreasing systematic pressures.
Now I will talk about the theory that enabled us to achieve our objective. In this experiment, we utilize equilibrium and kinetics effect to quantify the adsorption capacity of a specific adsorbent, the substance that will adsorb the gas. In our case, it will be activated carbon with very high surface area. You can see here the real and the schematic picture of the setup. To accomplish a spontaneous flow of our gas toward the adsorbent, we first flush the system by argon gas to ensure an equal chemical potential of both sides. After that, we pressurize the section on the left with our adsorbed gas, and according to the free Gibbs Gibbs free energy for pure gases, which can be assumed as an approximation, the chemical potential on the left will increase, leading to a spontaneous flow from the left to the right of the gas, according to the kinetic theory and the random motion of molecules. The system will eventually reach an equilibrium state, and the pressure in both sides will be equal. The amount of gas adsorbed on the activated carbon can be quantified at this equilibrium state using the virial equation of state that relates known quantities and measured quantities such as the pressure, volume, and temperature, and this will enable us to calculate the number of moles of gases. By calculating the number of gas adsorbed, we can now characterize the behavior and the relationship of adsorption process between the adsorbent and the adsorbate by trying to fit the data to adsorption isotherms plots, in which the concentration of the adsorbate in the adsorbent particle denoted by W is plotted against the concentration in the fluid gas denoted by C. In this experiment, we will fit data to three common isotherms: the French-Lich isotherm, the Langmuir isotherms, and the Sibbs isotherms.
Results and data analysis. Pressure readings for the entire pressurization process and depressurization process were recorded for each chamber. They are as followed. The first step was to calculate the number of moles of each gas. In order to determine the number of moles of each gas present in each step, the Vriel equation could be utilized. The second Vriel coefficient, B, could be calculated according to the following equation, where T equals the average temperature. The average temperatures were determined from the data set as follows. These values were used to determine the second Vriel coefficients for each gas. Using the second Vriel coefficient and the recorded values from the experiment, the number of moles present in each chamber during each pressurization and depressurization step could be determined. The moles in chamber 1 and 2 were added together, resulting in the total moles at each step. The same method was employed to calculate the moles at the equilibrium step. The incremental adsorption was calculated by subtracting the equilibrium moles from the total moles in each step. This value corresponds to the number of moles adsorbed onto the carbon during pressurization, and number of moles desorbed during depressurization. The incremental moles adsorbed were summed and multiplied by the molar mass and converted to grams, resulting in the mass of gas adsorbed. Next, the value of W needed to be determined, which was the total milligrams gas divided by 10 grams of activated carbon. Graphical analysis. The values for W were graphed along the pressure of the gas within the volume 1. They are as followed. The adsorption data was fitted along using three different methods of Langmuir, Freundlich, and Sibbs. For both gases, the Freundlich model seemed to fit along the best in terms of slopes and rise in Q values. The Freundlich model allows for growth without a denominator section, which explains the rapid increase in adsorption of the model.
Despite their high surface area, activated carbon has a closed pore system, which means that its pores are not connected, and this can hinder gas molecules to reach active site on the carbon for adsorption. Hence, as a recommendation to improve the performance of the adsorption in this experiment, we instead of using activated carbon, we propose to use a hierarchical porous carbon as a gas adsorbent. In this hierarchical structure, three pore sizes are incorporated in the system. Macropores that has diameter larger than the 50 nanometer, mesopores diameter 2 to 50 nanometer, and macropores that has diameter less than 2 nanometer. The synthesis method of this material utilizes hard and soft templation to create those different sizes of pores. The purpose of incorporating macropores is to use them as a reservoir for gas molecules, which can help decrease the diffusion distance to the active sites. For the mesopores, they provide as you see here in this figure, they provide a low resistance pathway for gas molecules to reach the active sites, which are the macropores. The difference between this hierarchical porous carbon and activated carbon is the mesopores and the macropores. In activated carbon, there is only macropores. However, in hierarchical porous carbon, there is mesopores and there is also macropores, which can help direct gas molecules to reach the active sites, and this will increase the adsorption process or efficiency.
While we have been discussing adsorption, there's a similar process called absorption that we have not discussed yet. The main difference between these two processes is that adsorption is a surface-based process where only a thin layer of adsorbent is created. On the other hand, absorption is the process in which a fluid is dissolved by a liquid or a solid absorbent. This deals with the entire volume of the absorbing substance, unlike adsorption, which is surface-based. During this laboratory, we make use of the van der Waals equation of state, which is necessary as it leads to a more accurate result compared to the less accurate ideal gas law. Since our system has a high concentration of carbon dioxide, a more complex equation of state is necessary to account for the non-ideal actions of the adsorbate. Furthermore, there are several different characteristics one looks for when choosing a good adsorbent. This includes the ability to bind to as many ions, atoms, or molecules to its surface as possible. This requires a large surface area and high porosity. A strongly favorable adsorbent can be defined as having low concentrations with high adsorption per gram of the solid. Lastly, there is a parameter called B, which is dependent upon pore size, surface area, as well as the material properties. A high B value is associated with large adsorption.